All right. Okay, listen up. Okay, I think you're going to like this stuff for today. You will have seen some of it before. A lot of it is just vocabulary. So here's our goal for today. We want to understand, use, identify, and define vocabulary for circles. So the first question is a pretty broad one. What makes a circle a circle?
Round. 60 degrees.
What?
Round.
Can anybody do anything other than round? Yeah.
No, at corners.
No corners.
Actually, there's 360
Okay.
corners.
Need your hand up. Yeah.
The distance is always the same from the middle.
Okay. Distance always same from middle, and I'm going to change that to center if that's okay. What are the important parts of a circle? We're going to switch gears. What are the important parts of a circle? You know what circles are. Important parts of a circle. Luke.
Diameter.
Diameter. I'll take that. Okay. What else?
Radius.
Radius. Radius, which is related to the diameter. We'll see that in a second. D. Circumference. Very good. Okay. All right. We're going to move on. There's one other thing that you're going to find is super important about circles. What makes a circle the same or different from other circles? So if I have a circle over here that's this big, and I have another circle over here that's this big, what's the difference between those two circles? Yeah.
The radius.
Okay. Could be the size. Okay. What else? Let me do it again. What if I've got a circle that's this big, and I've got another circle that's this big?
Maybe they're different colors.
Okay, they could be different colors, not quite what we're after. Yeah.
Where it is.
Where it is, okay? So I'm going to put size and location, okay? You guys are doing really well. So let's talk about what a circle is. A circle is a set of all the points that are equidistant. So write the word equidistant. It is a word, okay? So they're equidistant from a given point, and that given point is called the center, okay? So equidistant just means, kind of like it sounds, equal distance. So we've got this center point right here, and I'm going to put an A right there, and all of these are exactly the same distance. Every single one of them is the same distance. So I could do something like that. That doesn't do it justice, but that's the definition of what a circle is. It's a set of points that are equidistant from a given point, and the given point is called a center. The radius is any segment with an endpoint at the center of the circle and the other endpoint on the circle. So it can't end part way. It can't end past the circle. It's got to be right here. So AB, like this, is a radius. Radius. Okay, and when we name circles, we call this circle, we name it by the center, so we call this circle A. Okay? So if it had a different center, center B, we'd call it circle B, and so forth. So here's the key idea. Would you put a star by this?
Yes.
This is going to be important in this unit, and it's going to be important in the next unit. Where the circle is, in other words, where the center is, and how big it is, in other words, what is the radius, gives us all the information that we need to know about a circle. Those are the two most important things. Where is the circle? Usually located on the XY plane or something like that. Okay, and how big is it? Is it a really huge circle? Is it a tiny one? What is that? Those are the two most important pieces about a circle. But if we take a look at how other lines, segments, angles, and shapes interact with circles, that can be really, really useful, and we can figure out a whole bunch of really cool stuff by knowing how these lines and shapes and angles interact. So the first thing we're going to define is something called a chord. So a chord is a segment. I know it's underlined, but would you double underline that? It's a segment. A chord is a segment. That means it's got two endpoints. So both of the endpoints are on the circle. It doesn't go on forever. So this would be chord ED. Okay? It's not a line, it's a segment. It's got two endpoints. Okay? A diameter is a special chord. So it's a special segment that passes through the center of the circle. And if you think about this, the diameter is actually the longest chord. So if I did something like this, that's still a chord, that's still a chord, That's still a chord, but the way we get the longest chord is by going from one side to the other side of the circle right through it. So this would be diameter CB. CB. Now, just going to make that look like a B. Remember, when we put that little line segment above there, it's got endpoints on it. If we wanted that to be a line, we would put arrows on each one of the endpoints. Okay? So next thing, this is called a central angle. A central angle intersects the circle in 2 points, and it has its vertex at the, no surprise, center of the circle. Okay? So what that means is this angle right here, because that's the center angle, so we've got a central angle, and it would be angle BAF, or FAB if you wanted to write it like that. Okay, and we're going to be using these words a whole bunch, so make sure you catch these. This is an inscribed angle. So here's what an inscribed angle is. An inscribed angle intersects the circle in 2 points, and it has a vertex on the circle. So it's not inside the circle anywhere. It's not outside the circle somewhere. It's right here. So the fact that this vertex is on the circle, that makes this an inscribed angle. Okay? So angle DBC is inscribed in circle A. Okay? That's how we'd say that. Luke, you had a question?
What does scribe mean within the concept of math? Because it's used a lot with different prefixes throughout the paper.
When you scribe something, you draw it. Okay? So inscribed, drawn inside. We're going to come up on some words in just a second. We've got circumscribed. Circumscribed would be drawn on the outside. Good question. Yeah.
When you're like drawing the circle figure, do you have to put the dot in the center?
You usually do. Yeah, that's usually what they look like. Okay, because it kind of emphasizes we name circles according to where the center is. Okay, so by putting the dot right there, everybody knows that that's where the center is. Okay, and then let's talk about this word scribed again. A polygon that is circumscribed by a circle, okay, has all of its vertices on the circle. And the polygon's interior is completely within the circle. So the circle is entirely on the outside. The polygon is entirely on the inside. And there are kind of two ways to say this. So circle A is circumscribed about the quadrilateral. You can see that this circle right here, with its center of A, is circumscribed. It's on the outside. So circumscribed is it's on the outside. And then the next one says an inscribed figure is a shape that is completely enclosed within another shape. So in other words, it does this. It fits snugly inside. So you can kind of match them up this way. Circumscribed, it's on the outside. Whatever does the circumscribing, it's on the outside. If it's inscribed, it's on the inside. Okay? So in our example right here, this quadrilateral is inscribed in circle A. So you've got the same diagram, but you've got two ways to say it. The circle is circumscribed about the polygon, so it's on the outside of the polygon. Or you could say it the other way, from the polygon's perspective, the polygon is inscribed inside the circle. Okay, everybody get that? Circumscribed is going to be on the outside, inscribed is going to be on the inside. Okay?
Gotcha.
Let's talk about a tangent. A tangent line intersects a circle at only one point. And the point where it touches the circle is called the point of tangency. Oops, tangency. So, BC, and I'm going to put a line right there because that's what it is tangent to circle A. And B right there, that is the point of tangency. That's where it touches. So this is the tangent. It only touches in one single point. And that's the point of tangency. Okay. Next one. Secant line, and notice that we've talked about chords, things that have endpoints, segments. The tangent line is a line. I suppose you could have a tangent segment. It would still have similar properties. A secant line is a line that intersects a circle in 2 points. So here's our example right here. So we could say secant BC, and we'd put lines over those. So my question for you is this. What's the difference between a secant line and a chord? Colson.
Chord stops if the circle has a secant line continues going down.
Very good. Chord stops. End points. And I'll just say on the circle rather than adding them. And then a secant line goes forever. Okay, everybody good with that? Okay, this first page is a bunch of vocabulary. Now, some of that vocabulary you would have seen before, some of it you would not have. So we're going to flip the page over and we're going to take a look at these. I did add this one right here. So as I was looking at this morning, I realized we left off one. Okay, this is a secant. Now, what I need from you before, so we can finish this in time is I need this. Make sure you're paying attention. It says identify each of the following. When more than one answer is possible, put more than one. So, chord. Don't shout it out. I need somebody to raise their hand and give me a chord. DNJ.
BD.
BD. I like that. BD. So I'm going to do BD and I'm going to put a segment over the top of it. So we got that one taken care of.
Yes.
Lizzie. CG.
Well done.
CG. Perfect. C to G. Does it matter if I did CG or GC? Nope.
No.
Any others?
No, yes, C.
Okay, we'll skip that for the time being. Tangent line. Jack.
HG.
HG or GH. And I'd put lines on the end of that. Diameter. Wilson.
CG.
CG.
No.
What?
Oh, yes.
Yep.
I was
Okay.
thinking radius.
Radius. Crew.
AE.
AE. I'll take that. Whoops. AE. I'll take that. Dane.
AC.
AC. I'll take that. Sai.
AG.
AG. Any others? Okay. Point of tangency.
G.
Just G. Center. Just A. Central angle.
Oh.
Yeah.
I need hands up.
Wait.
Luke.
GAE.
GAE. Got that. GAE. Anybody got another one? Crew.
CAE.
CAE. Okay. Yeah.
Wouldn't CAG also be?
Ooh. CAG. Angle CAG. Would that do it?
It's one of those.
It would, because it is a central angle, but it's a straight angle, right? 180 degrees. Nice job there. Secant line. This is the one that we left off. It's not on your paper. Secant line. D. JF is a secant line. So JF is a secant line. Okay, everybody convinced we got them all? Okay, now, could somebody make an argument that segment JF is also a chord?
Yes.
Could we lop off the ends of the secant line and make it a segment?
Yes.
And then it would be a chord.
Yes.
So I'm going to put question mark, and we could say, yeah, if you wanted to do JF, but you better put the line over it so everybody knows, hey, it's not a line, it's just a chord. Would we probably include that on a test? Probably not, because they're talking about what's the best possible answer. Yeah.
You can just lop those off. Couldn't you like lop them on segments to make them
Lop them on.
Yeah.
I'm not sure lopping on is a real word, but if you want to make it one in your world, that's fine. Okay. Again, no talking out loud. I need you to look and think. Raise your hand if you know. Notice that this says identify the term that best describes. Not that It'll work. Best description for AF. Zach, diameter I think is the best description. Sure, it's a chord, but diameter is the best description. C. Samara. Yep, point of tangency. Point of tangency. What about EG? Best name for EG. Caleb, what do you got? It is just a chord. That's about as special as it gets. CE. Look carefully. CE. It's got a line through it. That. Probably the best name for that because it's a line is a secant. Okay? Secant. PF. Megan, what do you think? From P to F.
A radius.
Radius, perfect. Radius. Notice the lines. BD. Lydia, what do you think on BD? Tangent, very good. Tangent line, I like that, adding the line. Tangent line. PC, notice that it's got end points. There aren't lines on the end of that. Luke?
Radius.
Radius. And P? Oh, Sai's hand nearly pulled his arm out of his socket. What is it? Center. Okay, now, you're going to be thankful that you don't have much like this. So I need, just chill out. I need you paying attention for just a second. Okay, you saw last week that there were dozens, if not hundreds of different.
Mr. Lott,
Yep.
I need Ryan McDougall. She's checking out.
Okay.
Thank you.
You saw hundreds of different proofs of the Pythagorean theorem. Some were ridiculously complicated. Some were really, really just beautifully simple and stuff like that. I want to show you a proof here. Okay, so here's what the proof is, and then we're going to kind of make things a little bit easier. A proof that all circles are similar. So figures that are similar have corresponding parts that are proportional. They're not congruent, they're proportional. And there are a bunch of ways to show that all circles are similar to each other. The only thing that's different is their size. Same shape, different size. Okay? So below is a paragraph proof. Now, we haven't done a paragraph proof. We've usually relied on two-column proofs. Those are a little bit more typical in geometry. But if you want to write out your thoughts line by line that people can follow, then that would be okay. So that's what this is. So I've got two triangles. Again, we don't go by the way things look, but it looks like circle A is a little bit bigger than circle D. So here's what we start with. It says angle A is congruent to angle D. So those are already marked. I'm going to mark that again. We've got that for sure. And it says the radius of circle A is X and the radius of circle D is Y. And it says prove that circle A is similar to circle D. Now, all I want you to do is just kind of follow along with the logic here, and then I'm going to show you what I think is a much simpler way to do this. Okay? So, AB is congruent to AC. AB is congruent to AC. So I'm going to put a mark here and a mark here. And I don't think they included this very well, and the reason for that is because they're both radiuses. Or does anybody know the plural for the word radius? Luke?
Radii.
Radii.
Radius.
Okay? They're both radii on the same circle, so they've got to be congruent. Which makes triangle ABC an isosceles triangle, so that's isosceles. So that makes angle B and angle C congruent, so I'm going to mark those as congruent. Can somebody tell us why those are congruent? Mason?
We know they're the same length system as X.
We do, and congruent sides are cut by congruent angles, and those are called base angles. Base angles of isosceles triangles are congruent, which if you'll notice is the exact same wording for this stuff. So again, those are radii. It says that the triangle over here on circle D is also isosceles. So that means that these two base angles, I'm going to mark them with two arcs. Whoops, I need to do this. Two arcs on this because we already used one arc. I need three arcs on these. Okay? So that means that those base angles, angle E and angle F, are congruent. Isosceles triangle here in this circle, isosceles triangle here in this circle. So if you take angle A and angle B and angle C and add them all up, you get 180 degrees. So add the angles in this triangle together, you get 180. Add the triangles or the angles in this triangle together, you also get 180. The reason for that is the triangle, very good, triangle sum theorem. We use it all the time. The technical name for that, the fact that inside every triangle is 180 degrees, it's called the triangle sum theorem. Okay? Now take a look at this line. There's the A, there's the 180. Now it's got two B's instead of a B and a C. There's the D, there's two E's. This better be 180 degrees. What did they substitute? The fact that angle C is the same as angle B. So they just made this angle B, and they made this angle E, because they're congruent. They just substituted. Everybody good with that? Solve for A on this one, so move that over. Solve for D on this one, so move that over. And here's what you get. Angle A is 180 minus 2 angle B's. Angle D is 180 minus 2 angle E's. And the reason we did that, that's just some algebra, just moving some things around in an equation. And since they said in the given those two angles A and D are congruent, we can do some substitution and just set this equal to this, and then we can solve. And if you solve, you can drop the 180s. You can divide both sides by -2, and what do you end up with? Angle B is congruent to E. So I'm going to come back here, and I'm going to mark this. I'm going to put 3 arcs in each one of those. So this triangle right here, whoops, come back here. That angle is the same as that angle, and these angles are the same as those angles. So if A and D are congruent, and B and E are congruent, then the triangles have to be similar by angle similarity. And since the triangles are similar, then the sides are proportional. So if we did AB over DE, we'd have X over Y. And that's also the radius over the radius, which is XY. So therefore, they are similar. Okay? Now, that's horrible.
Yeah, I agree.
That sucks.
That was awful.
Okay?
You're gonna have us do this on.
Most of your assignment is stuff like this. Was that okay?
Yeah,
Okay.
I guess so.
I'm going to come down here and I'm going to show you a different way. So the thought question says this. It says, can you think of a way to prove that all triangles are similar using dilations and translations? So here's what I'm going to do. I'm going to take this circle A and I'm going to translate it so A is right on top of D. So I'm going to put them right on top of each other. I'm going to make them have the same center. Does that sound okay? So translate circle A, so A is on D. Got it? They're right on top of each other. So I'm just going to slide it over so they're on top of each other. And here's the tricky part. Dilate circle A by, you ready for this? Y over X.
No.
Okay, watch carefully. I'm going to change colors. If I slide these so they're right on top of each other, and then I dilate it, so I'm going to change the size of it, stretch it, shrink it, whatever. I don't know what the numbers are. I don't know if I'm making it bigger or smaller. But watch what happens if I take the size of this and I multiply it by Y over X. What happens? What happens? What happens? Mason.
We get Y.
We get Y. So we've just dilated it. So not only is it on top of D, it's the same size as D. And if it has the same center and the same radius, isn't it the same circle?
Yes.
So the only thing we have to do is just dilate it and move it around. Yeah.
I mean, how would a circle not be similar to all other circles since the only thing that you can really change is its position? and stretch it. You
I
can't
get it.
change
I get it. I get it. But we do this because mathematicians are weird. So do you like my weird way of doing this, or do you like their weird way of doing this?
There's
Cool.
Okay, theirs, definitely. Okay, all right, take a look. So here's the idea. Everybody watch. We have two circles. One has a radius of 3 and one has a radius of 5. If you're going to prove that things are similar, their corresponding parts have to have the same ratio. So would everybody agree that we've got a ratio of 3 to 5 on these two circles? One's bigger than the other. Okay, watch. So if we do radius, diameter, and we do circumference, radius is just radius. This is 2 pi r, and this, whoops, circumference is 2 pi r. This is just 2 times r, and then this is 2 pi r. So watch what happens if I plug in a 3 for the radius and a 5 for the radius. What's the ratio? 3 to 5. Does it match? Yeah. What if I do 2 times 3 times 2 times 5 for the bigger one? If I simplify this, what ratio do I get? 3/5. If I do it for the circumference, so this is how far it is from the center to the edge, how far is it from side to side. If I do, hey, I'm going to compare the corresponding parts, I'm going to compare the outsides. 2 pi times 3, 2 pi times 5. Cancel the 2 and the pi, what do I get? 3/5. Are all circles similar to other circles? Yes, they are. Okay? Would you circle how you're feeling about this right now? Not necessarily the proofs. We are going to do some constructions later.
Why is pi pi?